So today I'm going to be talking about rational functions, how to find the domain, range, intercept, asymptotes, and graph of a rational function. Finding the domain of a rational function is easy. Remember, the domain is essentially just asking what values of x will work for a certain function. Now, we could just start plugging in numbers, but we would quite literally be here forever if we did that. Instead, what you can do is figure out what you can't put in, and in the case of rational functions, anything that makes the denominator 0 is a big no-no. Essentially, what we're saying here is that the function does not exist at these places. Therefore, the domain is all real numbers except for those ones. You can find those values using 3 basic steps. 1. Simplify the function as much as possible and factor the denominator if you can. 2. Set each part of the denominator is equal to 0. And 3. Solve for x. Alright, so let's go ahead and take the example f of x equals x minus 5 over x squared minus 4x minus 5. Once we're all done factoring, we'll come out with x minus 5 and x plus 1. Now we'll set x minus 5 equal to 0 and x plus 1 equal to 0 and solve for x. We end up with x equals 5 and x equals negative 1, so these will be the values that we exclude from our function. But wait! There's another thing we need to note about these x values that make the denominator 0. They're either going to be a whole or a vertical asymptote. A whole means that somewhere in f of x you're going to have a 0 over 0, and it'll cancel out. So as we can see with our example here, we have an x minus 5 over an x minus 5, which cancels out and tells us that x equals 5 is a whole. But what about vertical asymptotes? Well, a vertical asymptote means that somewhere in f of x there's a 0 in the denominator that doesn't cancel out. In our example, we have this remaining x plus 1 that we can't do anything with, so we know that x equals negative 1 is a vertical asymptote. So let's go ahead and see what this will look like on a graph. We have our whole at x equals 5, and we got our vertical asymptote at x equals negative 1. We go over here to negative 1, and we go boop, 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 boop. Got our dotted line, boop, 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 boop. And we know that the graph cannot exist there, so it's going to narrowly avoid it like this. But don't forget, we still have to add our whole at x equals 5. So we go over here, let's get the eraser size down a bit, and there we have our whole. Typically, you'll write the answer in interval notation, which will end up looking like this. We're not going to have any brackets because any numbers we include in here are not included in the function. So now let's move on to the range. The range of a rational function is going to be pretty much just like the domain. It'll be all real numbers, except for the horizontal asymptote or the slant asymptote. In order to find a horizontal asymptote, we need to take a look at the leading degrees of the rational function. So let's say we have the rational function of f of x equals p of x over q of x, where n equals the leading degree of p of x, and m equals the leading degree of q of x. The following is what indicates where the horizontal asymptote lies. If n is less than m, then f of x has a horizontal asymptote at y equals 0. If n equals m, then f of x has a horizontal asymptote at y equals the leading coefficient of p of x over the leading coefficient of q of x. If n is greater than m, then f of x has no horizontal asymptote. Now let's look at some examples. Going back to that first example, we see that the top has a leading degree that is less than the leading degree of the bottom, which means that we have a horizontal asymptote at y equals 0. Simple as that. Going back to our graph, we see that this makes sense. We draw in our horizontal asymptote at y equals 0, boop, 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 and we can see the behavior of the graph lines up exactly with what we'd expect from a horizontal asymptote. And in interval notation, this is what the range will be. So let's look at another example. This time we have f of x equals 4x minus 2 over x plus 3. Here we can see that the leading degree of the top is the same as the leading degree of the bottom. So our horizontal asymptote will be at y equals 4 over 1, which of course just equals 4. Once again, it's real easy to plot out. We got our horizontal asymptote at y equals 4, so we go up here to y equals 4, boop, 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 and we have our horizontal asymptote. Now we'll take a look at f of x equals 3x squared plus 2 over x minus 1. But as we can see here, the leading degree of the top is greater than the leading degree of the bottom, so we don't have a horizontal asymptote. That being said, however, that doesn't mean we don't have another type of asymptote. See, if the top has a leading degree that is exactly 1 greater than the leading degree of the bottom, then there will be a slant asymptote, which is also known as an oblique asymptote. You find a slant asymptote by dividing the top by the bottom. Your quotient will be your slant asymptote. It's important to note that if you end up with a remainder, the remainder will not be a part of your slant asymptote, just the quotient. So let's go ahead and divide 3x squared plus 2 by x minus 1. Alright, so we end up with 3x plus 3 with a remainder of 5 over x minus 1. So our slant asymptote is at y equals 3x plus 3. Remember, we don't need that remainder. Now you may notice that this format is familiar. This is just a normal linear equation. So we'll start by plotting our y-intercept, which is 3, and then we go up 3, 1 over, and then down 3, 1 over, down 3, 1 over again, so on and so forth, and then we can draw our line. But that's not the only asymptote we have here. If we go back to our equation, we see that we have x minus 1 in the denominator, which, as we learned, will end up being a vertical asymptote since it can't cancel out. So we have a vertical asymptote at x equals 1. So let's go ahead and plot that. Boop, 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 boop. All right. And we end up having a graph that'll look something like this. We got a little cramped here up at the top, but you get the idea. Now let's talk about the intercepts. In order to find the x or the y intercepts, you'll set one variable equal to 0 and solve for the other. For the y-intercept, all we have to do is take our equation here and set the x value to 0 and solve for y. And we'll end up with the y-intercept being at 0, 0. Now, in this case, we actually already know what the x-intercept is going to be. Since y turns out to be 0, and that's the number we were already going to plug in to find what x would be, we know that the x-intercept is also at 0, 0. But I'll go ahead and work it out just to prove it. So we set the y value equal to 0, and we solve for x. And exactly as we thought, our x-intercept is at 0, 0. All that's left to do now is put it all together. We'll use the same function as last time, which is f of x equals 3x over x minus 9. The first thing we're going to want to do is find and plot the asymptotes. So we'll factor out our denominator real quick. We get x plus 3 and x minus 3, which means that we have vertical asymptotes at x equals negative 3 and x equals positive 3. And since the leading degree of the top is less than the leading degree of the bottom, we have a horizontal asymptote at y equals 0. So let's go ahead and plot these out. And of course, we already found the intercepts, so we'll just go ahead and plot those out. After that, you'll want to find and plot one point on each side of each vertical asymptote. We'll do this by picking x values and plugging them into the function to get their corresponding y values. So on this vertical asymptote, I'm just going to go ahead and take negative 4 from the left side and negative 2 from the right side. We'll go ahead and write that out, of course leaving the y spot blank for the time being. Now for this vertical asymptote, I'm going to do the same thing. I'm going to go ahead and take 2 from the left side and 4 from the right side. This is going to take a while, so let's speed things up. And now we have our y values. We'll go ahead and write those down where we can see them, and then we will plot them out. Start with this first one, we'll go -4, 1, 2, 3, 4, and then down to -12 sevenths, which is right about there. And we'll go to this next point, we'll go 1, 2, and then up to 6 fifths, which is right about there. And this next point is 1, 2, and then -6 fifths, which is right about there. And then this final point will be 1, 2, 3, 4, and 12 sevenths, again, right about there. And now we just have to draw the graph. It'll end up looking something like this. Now I went ahead and went in Photoshop and made this look a lot neater, and the end result ends up looking more like this. So yeah, that's all you need to know about rational functions. Sweet.